Today in section 3.4, scientific notation, we're going to perform operations with numbers in scientific notation. Now, before we do this, we'll be introduced to scientific notation and we'll work with that a little bit. And then once we become a little bit more comfortable, we will go on and perform operations and compare these numbers. We have two main math practices that we're going to use in this section. The first one is attend to precision. We're going to use that when we are first learning about scientific notation. We're going to be converting numbers from standard form, which is just a regular number we're used to scientific notation, which is what we are about to learn. So we're just going to have to be very careful and make sure we're being very exact in what we're doing. The other math practice we're going to use is look for and express regularity in repeated reasoning. So we're going to have kind of some patterns that we see as we go through and we solve these problems and we perform operations with these numbers. And that repeated reasoning is going to help us to do these problems faster and become more familiar and just more confident with them. So let's go ahead and talk about scientific notation. First of all, a number in standard form would be just something like 3,432, for example. That's just a normal number that we're used to. However, that number in scientific notation would be 3.432 times 10 to the third. So what this is saying is, first of all, we have 10 to the third, which is 1,000. So this is telling me that I have 3.432 times 1,000. And if I were to calculate this out, or I can even use a calculator to figure this out, I'm going to go ahead and do this. I have 3 zeros, and then 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, and 1 times 3 is 3 again. And I have 1, 2, 3 decimal places that I need to put in here. So this number, if I multiply that out, is 3,432, which is the standard form. So this is the notation that scientific notation is written in, and it's always going to be this same thing. So that notation will be this: a number times 10 to an exponent. So we're always going to have a number here. It's always going to be times 10, and then it's always going to have an exponent connected to the 10. So what do these numbers mean exactly, and what can we use to make it correct? Well, when we're talking about this number right here, that number has to be between the numbers 1 and 10. So it has to be the two numbers that scientific notation, meaning this number right here, must lie between are 1 and 10. The exponent, so now we're talking about the exponent over here in scientific notation, represents, I'm going to zoom in to write, the direction and the number of times the decimal moves. So this is strange. This is kind of a weird way to write numbers. Why would we do this? Why do we write in scientific notation? Well, it's a way that we can represent really, really, really big numbers or maybe really, really, really small numbers in a simpler way. So this is used a lot in science when we're talking about really long distances or really, really tiny molecules or atoms. We use this instead of writing out all the zeros and all the decimal points and everything. So scientific notation is a way to represent really large numbers or really small numbers in a simpler way. So what this tells us when we're looking at the 10 to an exponent, the main thing that's telling us is how much our decimal moves. So really all that we're going to be doing when we're converting between numbers is we're going to be moving the decimal around. So let's just think about our powers of 10. So let's go through this pattern. If it helps, think about 3.1, that section. Think about the fast-growing plant activity that we did. 10 to the first is just 10. 10 to the second is 10 times 10, which is 100. 10 to the third is 10 times 10 times 10, which is 1,000. And then 10 to the fourth is 10,000. Now there's a couple patterns that you notice here. Every time that we increase our exponent by 1, we multiply the number by 10. Another thing that you might notice is that the number of, or what the exponent is the number of zeros. So 2 exponents, 2 zeros. Or an exponent of 3, 3 zeros. And then 4, there's 4 zeros. So using one of these patterns, what is 10 to the 0? Well, if we go backwards, we're going to divide by 10. So 10 to the 0 would be 10 divided by 10, which is 1. Or we could see that there's 0 zeros, so there's just a 1. We can't write any zeros with that. Remember that any number to the power of 0 always, always, always equals 1, unless that number is 0, then it's 0. Otherwise, any other number in the world to the power of 0 equals 1. All right, going on to negative exponents. As I continue moving down my pattern, I'm going to continue dividing by 10. So 10 to the negative first is 1 divided by 10. 10 to the negative second is 1 divided by 100. And then 1 divided by 1,000. And 1 over 10,000. Also remember, a negative exponent does not mean a negative number. A negative exponent does not make a negative number. A negative exponent does make an inverse. It means inverse. And I say inverse instead of fraction because sometimes we start with a fraction and we end up with a whole number. So we need to be careful with how we word things. All right, so now we have kind of this foundation of our powers of 10, meaning all of these numbers here that we just came up with. And let's think about what happens when we multiply by these different numbers. Remember, scientific notation is a number multiplied by a power of 10. So if I multiply by a power of 10, that is greater than 0. So that's going to be any of these over here. If I multiply by any of those, my number is going to get larger. So my number is going to end up being greater than 1. It's going to get larger. However, if I multiply by an exponent that's less than 0, so a negative exponent, these over here, then my standard number is going to be less than 1. It's going to be smaller. Not negative, but it's going to be a small decimal. All right, so let's see what's happening here. Let's do some converting. Let's start by converting from scientific notation to standard notation. So this first problem, I have 5.8 times 10 to the 4th. Well, remember that my exponent tells me how many times it's moving, and it tells me which direction the decimal moves. So if the decimal moves 4 times, I need to think, is it going to move 4 times to the left or 4 times to the right? Well, it's positive, and if we look back at what we just wrote, we said when we have a positive exponent, our number is going to be bigger. It's going to get greater, which means that the decimal needs to move to the right. So my decimal is going to move over 1, 2, 3, 4 times. I have 3 spots that need to be filled, so I'm going to fill those with zeros, and my new decimal point is right here. So this number ends up being 58,000. If I were to multiply this out, I'd have 5.8 times 10 to the 4th. Remember that 10 to the 4th is 10,000. I have 4 zeros, and then 1 times 8 is 8, 1 times 5 is 5. I have 1 decimal that I need to move in there. I end up with 58,000. So that's what's happening here, but being able to move the decimal based on this number right here makes a huge difference for us. It's so much easier. Now, one other thing I want to point out is when we're looking at this exponent, we don't actually need to make these little bunny hops every single time that we're moving our decimal. I can look at this exponent of 4, and that tells me, okay, I'm going to move 4 times to the right because it's positive. Well, to the right of this decimal, I only have 1 number. I have this 8 right here. So that tells me that I'm going to have 3 spots left open because 4 minus 1 is 3. So I'm going to have 3 zeros. Let's go ahead and do another problem. 2.947 times 10 to the negative 3rd. Well, my exponent is a 3, which means it's going to move 3 times, but this one's negative. So that means it's going to make a smaller number. To make a smaller number, it has to move to the left. So my decimal is going to move 1, 2, 3 times to the left. It's going to be right there, and I have 2 spots to fill with zeros. So this is 0.002947. I could have also looked at this and thought to myself, hey, I'm moving 3 times to the left. If I look to the left of this decimal, there's just 1 number there, which means that I have 2 zeros that are going to have to be filled in, which is exactly what I have here. All right, just one more problem. Converting numbers like this. 3.107 times 10 to the 0 power. Well, my exponent's 0, which means my decimal is going to move 0 times. So if that's the case, my answer is going to be 3.107 because it's just not going to move. Well, if I think about what's happening here, I'm multiplying by 10 to the 0. 10 to the 0 power is just 1. So I'm really just taking 3.107 times 1, which is 3.107. Now the last thing we need to do here on these problems is we need to state whether these are greater than or less than 1. So let's go ahead and do that. This first one, I have 58,000, that is greater than 1. The next one is 0.002947, which is less than 1. And then this last one is 3.107. That is greater than 1. All right, I'm going to go on over, and now we're going to go the other way. We're going to start with a number in standard form, and we're going to convert it to scientific notation. So when I do that, remember, I'm going to need a number that's between 1 and 10 times 10 to an exponent. Well, to get that number that's between 1 and 10, I need to figure out where this decimal needs to go on this problem here to make it between 1 and 10. The only spot that I can put a decimal that does this is right here between the 2 and the 8. If I were to put the decimal anywhere in front of the 2, that number is going to be too small. If I were to put it anywhere behind the 2, that number is going to be too big. So the only spot is between the 2 and the 8. So this number is going to be 2.87. Those zeros that are at the end don't make a difference, because if I write 2.870000, that's the same thing as just 2.87. That's the beauty of scientific notation. Those extra zeros on the ends don't need to be written. So I have 2.87 times 10. Now I need to get my exponent. My exponent tells me how many times my decimal moves. So if my decimal had started at the end, because whenever there's no decimal in the number, that means it's just at the end, I need to figure out how many times it moves to get to that spot. So I'm just going to count it out. It moved 1, 2, 3, 4, 5, 6 times. So that means my exponent is 6. The last thing I need to think to myself is this a positive or a negative exponent? Well, this number, my standard form, is a big number. It's 2,870,000. So that's greater than 1. That is a big number, which means that this is a positive exponent. So my number in scientific notation is just 2.87 times 10 to the 6th. All right, let's go ahead and do the next one, 0.0000542. I need to figure out, first of all, where my decimal needs to go to make this number between 1 and 10. My decimal needs to go right here. The decimal is always going to go right after the very first counting number. So if I'm looking along here, my very first counting number is 5, if I'm looking left to right. And so it's going to go right after the 5. So I have 5.42. Once again, those zeros are not necessary to write, because 0.00054.42 is the same thing as just 5.42. And this is going to be times 10 to a power, and I need to figure out what that power is. So this decimal started here, and I need to figure out how long or how many spots it moved to get to here. So it moved 1, 2, 3, 4, 5, 6 times. But this time my original was a really, really small number. It was 0.0000542. And so if my standard form is small, then my exponent is negative. So my scientific notation is 5.42 times 10 to the negative 6th. I just have one more problem left, 83.537. I have a decimal in the middle of the number, but this is not in scientific notation, which is what I'm trying to do. In order to get this number between 1 and 10, the decimal needs to go right here, between the 8 and the 3. So this would be 8.3537. The decimal moved from here to here, so it moved 1 time. So this is times 10 to the first. 83.537 is a larger number, so my exponent is positive. So this is just 8.3537 times 10 to the first, or 8.3537 times 10. Either way, you can write it on this one. The next part that we need to do real fast is just state whether these have a positive or negative exponent. The first one has a positive exponent, second one is negative, and the last one is positive. All right, now we are going to move on to the back of this. Now that we have this solid foundation of what scientific notation is, we're going to go on and we're going to perform operations with scientific notation. So we're going to do some addition and subtraction, and then we're going to do some multiplication and then some division. So my addition and subtraction, I have a few steps that I need to go through for this. When I evaluate something like this, where I have a number in scientific notation plus a number in scientific notation, and I know that because I have a plus between those parentheses, my steps that I need to go through are these. First, I need to write my numbers in standard form. So I'm going to convert them to standard form. Once they're in standard form, I'm just going to add and subtract like normal. And then my final step, I want my answer written in scientific notation. So we're going to rewrite the problem, or rewrite the answer in scientific notation. So let's go ahead and do this. My first step is to write in standard form. So I'm going to take these numbers and I'm going to write each of them individually in standard form. So first I have 6.21 times 10 to the 5th. My exponent's 5, which means my decimal is going to move 5 times. It's positive, so my decimal is going to move to the right. Well, moving to the right, there's already 2 spots that are taken, which tells me I have 3 spots for zeros. So this is going to be 621,000. Next, I have 4.3 times 10 to the 9th. I need to rewrite that in scientific notation. Well, my decimal is going to move 9 times to the right because it's positive. 1 spot's taken, which means I have 8 zeros. So this is going to be 4, 3, and then 1, 2, 3, 4, 5, 6, 7, 8. And to break this up, I need to make sure I put my commas every 3 numbers. So 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3, comma. So this problem is 621,000 plus 4,300,000,000. There's a lot going on there. If you're not able to just look at that and know what it is, because there's a lot of numbers and there's a lot of digits in this, I'm going to go ahead and line my number, or line this addition up and down, and then work it out. So remember, when you write out addition up and down, your decimals need to line up. So this is going to be a 0, 0, 0. I need to make sure my commas are lining up so that I make sure I'm adding the correct digits. And now I can add this. So this is 4,300,621,000. And now my final step is to rewrite this in scientific notation. So if my decimal is right here, I need to figure out where that decimal needs to go in order to make this number between 1 and 10. Well, it's going to go after that first whole counting number. So it's going to go between the 4 and the 3. So this is going to be 4.300621. Notice I put those zeros in the middle. Those are important. You must have the zeros between whole numbers, but you don't necessarily need these zeros that are on the end. And then my decimal moved 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So this is times 10 to the 9th. And it was a large number, so this is a positive exponent. And that is my answer here. So when you are adding and subtracting, you're going to go through the same steps. You're going to write the number in standard form. You're going to work with standard form. And then you're going to rewrite the answer in scientific notation. Multiplication and division are a little different though. For multiplication and division, we're not going to convert back to standard form. We're going to just work in scientific notation. So our steps for this, for multiplication, are first, we're going to multiply the coefficients. When I say coefficients, I'm talking about the numbers in front of the scientific notation. So that's that number that's between 1 and 10. Next, we're going to multiply the powers of 10. The powers of 10 is, I'm talking about the number that is 10 to the exponent. So that's the other part of the scientific notation. When we do this, we're going to add the exponents. And then finally, our step number 3 is we're going to rewrite the answer in correct scientific notation. So rewrite in correct scientific notation. So let's go ahead and try this out. When I look at multiplication in scientific notation, notice that it's 2 times 10 squared times 6.1 times 10 to the 9th. So I just have a whole lot of multiplication going on here. I know that I can multiply in any order. That is my commutative property that I learned in Unit 1. And so that is why I can multiply the coefficients. That's why I can take those two numbers and I can multiply them. So I can do 2 times 6.1 before I multiply my 10s. 2 times 6.1, if I don't know what that is off the top of my head, I'm going to multiply over to the side. 6.1 times 2, 2 times 1 is 2, 2 times 6 is 12. I have 1 decimal, so I need to add 1 decimal to the answer. So this is 12.2. My next step was to multiply my powers of 10. So I have 10 squared times 10 to the 9th. I notice that I'm multiplying numbers with the same base. And so if I think back to section 3.1, I remember that when I multiply numbers with the same base, I add the exponents. So I'm going to do 2 plus 9, which is 11. So this is 10 to the 11th. And now I need to put this together. So this is going to be 12.2 times 10 to the 11th. So this is written in that notation, But this is not correct scientific notation because this number right here is not between 1 and 10. In order to get that number between 1 and 10, my decimal needs to move here. So I need to write this as 1.22 times 10, and my decimal moved over once, so I need to change my exponent. The final answer is 1.22 times 10 to the 12. But why did I make it 12 instead of 10? Well, the rule is moving the decimal to the left makes the exponent larger, which means you're going to add. So when you move to the left, you add. When you move to the left, you add. I want you to repeat that a couple more times. When you move to the left, you add. When you move to the left, you add. That is super, super important. When you move to the left, you add your exponent. So why do we do that? Why didn't I subtract it instead? Well, let's look at what this is. If I look at 12.2 times 10 to the 11th, and if I write that out as a number in standard form, I need to move my decimal 11 times to the right because I'm making it bigger. There's already one number there, which means I'm going to have 10 zeros. So I have 1, 2, 2, and then 10 zeros. I'm going to put my commas in. That's a really big number. Now, if I'm going to write this number in correct scientific notation, my decimal needs to go right here. So this is going to be 1.22 times 10, and my decimal had moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So this is 1.22 times 10 to the 12th, which is what we have there. So when you move to the left, you add. All right, so once again, when you multiply, you multiply the coefficients, then you multiply the powers of 10 by adding the exponents, and then you rewrite in correct scientific notation. Now let's do some division. With division, it's very similar. But instead of multiplying the coefficients, we're going to divide the coefficients. And then instead of multiplying the powers of 10, we're going to divide the powers of 10. Instead of adding this exponents, we're going to subtract the exponents. And then that final step, we will still rewrite in correct scientific notation. So let's go through this. I have 1.04 times 10 to the 8th divided by 2 times 10 to the 4th. So I'm going to take my coefficients, my numbers out front, and I'm going to divide them. 1.04 divided by 2, I'm going to write that over to the side so I make sure I keep track of my decimal and everything. 2 goes into 1 0 times, 2 goes into 10 5 times. I need to make sure I copy down that decimal. 5 times 2 is 10, which means I don't have any numbers left over. 2 goes into 4 2 times. 2 times 2 is 4, so I have no numbers left over. So 1.04 divided by 2 is 0.52. Next, I need to divide my powers of 10. If I take 10 to the 8th divided by 10 to the 4th, when I divide numbers with the same base, I subtract the exponents. So 8 minus 4 is 4. So this is going to be 0.52 times 10 to the 4th. Now, this is not written in correct scientific notation because of that number right there. So in order to write it in correct scientific notation, I need my decimal to be between the 5 and the 2. When I move my decimal over, I need to change my exponent. When we moved our decimal to the left, we added, which means when we move the decimal to the right, we subtract. So I did 4 minus 1 because it moved one time to get 3. So moving the decimal to the right makes the exponent smaller, which means I'm going to subtract. So the final answer here is 5.2 times 10 to the 3rd. When I move to the right, I subtract. When I move to the left, I add. So if that's kind of hard for you to wrap your head around, because that is a little different to think about, you can always go through the steps of writing it out to standard form and then writing that as scientific notation. So I can write 0.52 times 10 to the 4th as 5,200 because I know my decimal moves to the right 4 times, which leaves me with 2 spots to fill with zeros. And then 5,200, I'm going to write in scientific notation. So my decimal goes between the 5 and the 2. And then the decimal had moved 1, 2, 3 times. So this is 5.2 times 10 to the 3rd, which is the same. It's positive because 5,200 is a large number. Go ahead and pause this video and do these next 2 examples on your own as best as you can. And then once you're done, or if you get stuck, play the video and I'm going to talk through the problem so you can double check your thinking and you can double check that you did it correctly. All right, this example, 3.5 times 10 to the 3rd times 7 times 10 to the 8th. The first thing I need to do is multiply my coefficients. 3.5 times 7, if I do that over to the side, 7 times 5 is 35, carry the 3. 7 times 3 is 21, plus 3 is 24, and I have 1 decimal to add in there. So this is 24.5. And then I have 10 to the 3rd times 10 to the 8th. Well, I have the same base, so I'm going to add my exponents. 3 plus 8 is 11. So this is 10 to the 11th. This is not in correct scientific notation. I need to move my decimal over so that it's between the 2 and the 4. So I have 2.45 times 10. I moved it to the left, which means I add. I moved it once, so I'm going to add 1. So this is 10 to the 12th. And that is my answer. Next one, 2.4 times 10 to the 6th divided by 6 times 10 to the 11th. First, I'm going to divide my coefficients. 2.4 divided by 6 is 0.4. I need to make sure I'm being careful with my decimals. I could have done that over to the side. And I'll line up my decimals. 6 goes into 2 0 times. 6 goes into 24 4 times. Next, I need to divide my tens. 10 to the 6th divided by 10 to the 11th. I'm dividing with the same base, which means I subtract my exponents. 6 minus 11 is negative 5. Make sure you're careful with your positives and negatives. This is not in correct scientific notation. This decimal needs to move to the other side of the 4. My decimal moved to the right, which means I'm subtracting. It moved to the right 1, so I subtract 1. Negative 5 minus 1, I need to add the opposite, so this is negative 6. So I have 4 times 10 to the negative 6 on here. There is just one more part to this section, and that is comparing scientific notation. So with comparing scientific notation, we're just saying which number is larger between the two of them. We have 2 rules. Our first rule, and this is the main one, is you always look at the exponent first. The larger exponent is always the larger number. Rule number 2 is if the exponents are the same, then you compare the coefficients. So if you have to compare the coefficients because the exponents are the same, you're going to take the number with the larger coefficient. That's going to be the largest number. So let's go ahead and do these. 8.74 times 10 to the third compared to 8.74 times 10 squared. I'm looking at my exponents, 3 versus 2. 3 is larger, so this is greater than. Remember that your sign is always opening up towards the larger number, almost like it's trying to eat the larger number. So this is 8.74 times 10 to the third is greater than 8.74 times 10 squared. Next, 8.992 times 10 to the negative 6 versus 6.4 times 10 to the negative 4th. If I'm comparing negative 6 and negative 4 is larger, because I'm thinking about negatives. And so this is a less than sign. Next, 3.889 times 10 to the 4th is equal to 3.889 times 10 to the 4th. Next, 4.151 times 10 to the 5th and 6.8 times 10 to the 5th. I have the same exponent, which means I'm not looking at the exponent on this one. I need to look at the number in front. When I'm comparing 4.151 and 6.8, 6.8 is larger, so I'm opened up towards that. This is a less than sign. And finally, my last one, 7.382 times 10 to the negative 20th versus 7.4 times 10 to the 20th. It's the same exponent, so I need to look at the coefficient. 7.382 versus 7.4. Remember, I'm looking at this one number at a time. I notice that my whole numbers are the same. They're both 7, so I need to move over to the number right after the decimal. I'm comparing 3 and 4. 4 is larger, so 7.4 is the larger number. So this is a less than sign. That is all for this monster of a section. Great job sticking with me on this. You can now do your homework, and then, of course, as always, come talk to me. Let me know if you have any questions or you need any clarifications.